Hello, welcome to part 2 of the magnetism overview, and in this part I'm going to talk about permanent magnets, like the magnets you know from your fridge, or possibly for some kids' toys, like my son for example has these little train cars that hook together, or connect together magnetically, and if you turn them the wrong way around they're going to repel each other, for example. Let's talk about those kinds of magnets. Because ultimately we're going to be able to explain their magnetism, their magnetic properties in terms of moving charges, but we're not there yet. Right? Let's think about permanent magnets first. In fact, those have been known for centuries, if not millennia, and apparently the Chinese have known about permanent magnets and their properties for a very long time. And I think for the longest time it was a sort of nautical thing. Right? If you were a sailor, you knew about permanent magnets because you were able to use them for navigation. That's because of the Earth's magnetic field, which we're going to come to as well in this video. If you look at a basic bar magnet, so as long as a bar magnet, like you might be able to find them in any physics lab, say, but also maybe you've got one at home. Your fridge magnet is one of those, except very flat, sort of squished like this. It looks like this, and it has two poles, and we're going to call them north and south, but those are just names, right? You could call it the red pole and the green pole, or the up pole and the down pole, or Fred and Jim. It doesn't really matter, right? But they're called north and south because of the history that magnetic properties were first discovered in the context of the Earth's magnetic field and used for navigation. So if you have a compass needle is just one of those, a very small version of one of those, and the North Pole is called the North Pole because it points north. So, but I want to emphasize those are just like two names. And if you have more than one of those, and this is something you can do at home, for example, with the aforementioned sort of little toy train cars, if you have those, maybe you have a kid, or maybe you have a little cousin, nephew, whatever, you can do experiments, like when you say, okay, I'm going to take two of them and I'm going to put them together. If you put them together in this way, that the like poles, the north-north or south-south, and that they're facing each other, then they're going to repel. If you put them this way, that south is next to north, they're going to attract. So unlike poles attract, like poles repel. It's a little bit like electric charges, right? Two positive ones repel, two negative ones repel, but positive and negative attract. The difference here is that north and south poles, they always come together, right? You can't get a single north pole or a single south pole floating around. If you say I put one of those, say, on a side, it's going to flip. Right? It's going to flip one way or the other because one pole wants to be close to the so let's be specific here. Let's take this one, and I'm going to turn this one here, the bottom one, I'm going to turn it so the north pole sticks up. Then this pole, the north pole, is going to get attracted to the south pole of this one here, that's now like my pencil, gets repelled, so it's going to want to flip back. Essentially how compass needles work. Except that they do it with the Earth being the other magnet. So, as I already said, if you take a magnet and you try to cut it in two, and it can be difficult because magnets tend to be made of, iron and other iron-full metals alloys, you don't get a north pole and a south pole, you get two magnets. So that's very different from having an electric dipole where you have a plus and a minus, and I can just imagine they take them apart. They take one this way, the other one this way, it's totally fine. Nothing wrong with that. If you try to cut a magnet in two, you're not going to get a north pole and a south pole. You're going to get two smaller magnets, each with their own north and south pole. This result, we call it the no magnetic monopoles. And that means these poles, they don't act like electric charges, right? They sort of do in the sense of attract and repel, but they don't in the sense that they don't occur by themselves. And the fact there are no magnetic monopoles is, in fact, a very curious fact experimental fact, if you like, from a theoretical perspective. Because once you understand the full theory of electromagnetism, like all of electrostatics and magnetism and how they interact with each other, you see a certain symmetry, right, between electric and magnetic fields. But the symmetry suggests that just like there are electric charges flying around, electrons, protons, there should be magnetic ones. Like there's no inherent reason in the theoretical structure of electromagnetism that there aren't any magnetic monopoles. And this question of why aren't there any, why have we never found one, that doesn't go away when you ask about more sort of fundamental theories in terms of fundamental fields, as you have talked about them in particle physics, for example, and with quantum mechanics and all that stuff. It doesn't really resolve this underlying question, why are there no magnetic monopoles? It's an experimental fact that either there are none or they're so exceedingly rare in the universe that we've never seen one. Right? We've just never been that lucky. But because you look really hard, it means if there are any of those out there, they're really, 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 really hard to find. Unlike electric charges, which are absolutely everywhere. So this is a very sort of curious theoretical fact, kind of a question of why is it that there is no such thing as a magnetic so-called monopole. So that's an open question right there, right? Now, another thing about those normal permanent magnets is that they attract materials that are not magnets, right? They act on other magnets, but they also act on, say, an iron nail. Or your fridge magnet, you stick it to your fridge. The fridge is not itself a magnet. So what's going on there? So let me dive into that idea. So here's my big picture of a nail. Right? This is a nail. And if you zoom onto a nail, if you zoom in, you could not literally see, but you would sort of notice that the nail is made up of lots of tiny little magnets. I'm going to draw them as little arrows now because I'm too lazy to always draw north and south. So if I draw it like this, it's saying, look, there's a magnet here with the north pointing in the direction of the arrow. That's just a convention. So the nail might look something like this. It's made up of lots of tiny little sort of magnetic areas, and we call them domains. Actually, I wrote this down further down on the page, domains. But then they're not aligned, right? They point in all sorts of different directions. So you've got lots of tiny bar magnets. They're not just individual atoms, I have to add that. They're each made up of a whole bunch of atoms that sort of align with each other, forming magnets. But overall, right, some of the magnets point this way, some this way, some this way. There's no overall magnetic effect. But let's pretend we bring another big magnet, a bar magnet here. So this is South Pole, right? The North Pole is somewhere down in the corner down here. South Pole here. So now all the North Poles in here, they get attracted to the South Pole, so they flip. Right? You can imagine there being lots of tiny little compass needles that are gonna flip and point towards the South Pole. Maybe not all of them perfectly, like here I just drew a couple that aren't, perfectly straight aligned, but close enough. So what we're gonna get is an overall magnetic effect. Now they now all add up, those individual tiny magnets. Right? They add up to make one stronger magnet, namely the nail. And so now the north pole of this, all the little north poles point to the south pole, so the whole thing has the north pole pointing downwards, so it gets attracted here. If instead I put a north pole here, all those arrows would have flipped the other way, because their south poles, the individual south poles, want to face the south pole. So that means the overall nail would act like a magnet with the north pole up to the top right, the south pole bottom left, and because this is a north pole in that case, it gets attracted again. So it attracts both ways. Another thing you can do, and maybe you've done that, hopefully you've done that in some kind of middle school physics class, when you take a magnet and you sort of move it across the nail a couple of times with the same pole, you can make those domains align themselves semi-permanently. So then the nail just acts like a magnet in itself. It becomes a magnet. It's not a very good magnet, and it's not going to maintain that that magnetic property for forever, but it's gonna sort of stick around being a magnet for a while. If you then bash it with a hammer, the impact will give it a lot of energy at the atomic scales. It will move those domains again in all sorts of directions. Or another thing you can do is you can put it in an oven and it's going to demagnetize again. Why? Because putting it in an oven adds thermal energy. Thermal energy is kinetic energy of the atoms, so they move around more, which means they don't stay magnetized in this way. Right, so if you've got a fairly good bar magnet at home, you can try it. Just get a nail, make sure it's made of iron, and you can sort of stroke it. Like imagine this is my south pole. I might go like this. Again, lift off. Just a couple of times. I'm gonna turn the nail into a magnet. So if you haven't done this in middle school, say now is the time to do it. Okay. We're gonna come back to what those individual domains are. Like how do individual atoms each form tiny little magnets that group together in these domains. We'll come to that later. Okay, so now let's go back to a single bar magnet, north and south, and let's imagine I have a bunch of compass needles. Maybe just one needle that I'm moving around. Now, a compass needle is in itself just a tiny little magnet, but it's not very strong, but it's very light, so it's kind of like a probe magnet. Like remember, we had probe charges in electrostatics, and we thought of it as it doesn't really create its own electric field very much, a probe charge, but it reacts to the electric field that's there. Same thing with a compass needle. A compass needle is a tiny little magnet, yet it creates its own magnetic field, but it's very weak, it's very light, it mostly just reacts to the magnetic field that's there, created by whatever other magnet is around. So if I move my compass needle around, the arrow again, just like before, it always points in the northern end, right? If I put the compass needle here, the magnet, its northern end is going to flip away from the north pole here, and the south pole of it is going to get attracted. So north pole points away, south pole points towards here. If I move it around and I sort of record the direction, it's going to look something like this. If the tip of this pencil is the north pole, it's going to look like this over here, and look like this over here, this over here, this over here, and over here, right, the north pole, the tip, is attracted to the south pole of the magnet, so it looks like that. In the middle here, it looks like this. This pole wants to go there, but this pole wants to go there, and so they sort of fight, and nobody wins. Whereas if you're here, this pole, the south pole, wants to go here, but the north pole is way closer, so it kind of wins out, if that makes sense. So you do this enough, and you can see a certain pattern here, right? And if I do this pattern by sort of connecting those arrows, I can get something that looks like this. This is called a field line representation of the magnetic field. We had electric fields. This looks very much like the magnetic field, like the electric field, except these are magnetic field lines. Now, one thing I want to emphasize right now is that the magnetic force on something is not in the direction of the field line. It's different from the electric field. Right? Instead, our intuitive sort of definition of magnetic field is that that's the direction the compass needle points. Right? If I take a little compass needle, I want to put it right here, it's going to align itself this way. If I put it here, it's going to align itself this way. Right? That's the idea. There are certain rules to drawing magnetic field lines, and much like with electric charges, they can never cross. They don't ever start or end because remember, there are no magnetic monopoles. Electric field lines start or end at charges. But if there are no magnetic charges, no magnetic monopoles, they can't ever start and end. Now you say, but what about north and south poles? Don't they start and end there? It's sort of true, but if you were to look what's inside a magnet, you see that they all sort of curve around like this. They all kind of go through the magnet. The magnetic field inside the magnet is huge. So they also go around in just loops. They always form loops. Unless they go off to infinity, like this one here, they're gonna magnetic field lines always form loops. And again, much like in the case of electric field lines, the denser they are together, the stronger the field. So here the field is strong, all those lines are really close together. Over here the field is weaker, they're further apart. And they also kind of want to spread out from each other. So that gives us a visualization of the magnetic field. You can imagine if I've got more than one magnet, then you could draw the field then just from those rules. Let me show you a little example of that. Just let me draw it live here. Imagine I have a setup where I maybe have one magnet like this. There's north, south, and maybe I put a second one here. I say south, north, right? You can imagine just following those rules. They always so with the poles, right? Yes, they never end, but they do come out of north poles and go into south poles. But inside the magnet they connect the two. So I follow those rules. I might draw it something like this. So it comes over north pole, goes into a south pole. Maybe like this. Over here, this one might go back to this south pole. It goes here. This one might do this. Let's see how this so might go back to here. Just from the overall shape of the thing, I can sort of draw the rough estimate of what the magnetic field might look like. So really, as long as you're close to one magnet, it looks very similar to just the one magnet. But if you're sort of between the two, it's gonna look different, right? Here, those lines they enter the south pole right there, and some lines might come in from far away. It might probably look something like this. Let me just do another example for you. Let's say I again have two magnets. One magnet is boring, right? I have two magnets, and maybe they sort of look like this. I've got a south pole and a north pole, and then I have a north pole and a south pole. Right, so now I can imagine I get this kind of effect. Like the stumps stay really close. They just go out of the north pole into the south pole. But the ones over here, they're gonna do this, and conversely the ones here do this, and here. And again, just from the shape of it, you can probably tell that somewhere in the middle there's an area where the magnetic field is exactly zero. So if I put a compass needle right in the middle, it just wouldn't know where to point. I mean, realistically, if it really was zero due to those, it would then again pick up the Earth's magnetic field in the background, which gets overshadowed in a situation like this by the magnets that are present. Do one more here. Okay, there we go. All right, maybe one more here. So again, this just gives us the rough shape of the field, much like we were able to use electric field lines in electrostatics. Okay, so this was drawing magnetic field lines, and the magnetic field right now, remember, is just defined as which way does the compass needle point, and then we draw the lines, and the closer they are together, the stronger the field. So the more the compass needle will react, like the quicker, right? The stronger the force on it. The last little topic in the permanent magnets area is the Earth magnetic field, and here I drew a remarkably accurate, if slightly messed up Europe, but a remarkably accurate map of the Earth. Right, freehand from memory. I take great pride in my drawing here. I even include the Falkland Islands, Cuba, and Hawaii, Galapagos Islands, Greenland, Iceland, I don't know what else. Anyway, beside the point, right? So this is the Earth's magnetic field, and I drew the axis of the Earth being straight up, right? Of course, if the sun were like over here, then you should have drawn the axis more like this, but that's beside the point right now. The axis like this, the Earth spins like this. Now, you can say we are here somewhere, right? This is kind of Bellingham up here. You can imagine I have a compass needle, and I'm gonna look at it, and it points north. That's why we call it North Pole. right? Actually, one thing you notice is that if you actually have a compass, and please get one out if you do, you point, like it will point north, but if you hold the compass needles like so it's vertically, so it can go vertically like this, it'll actually point downwards. Let me do a little drawing here. So here's the floor, here is me, and I'm holding my giant oversized compass needle like this. It'll actually point like downwards into the ground, because the actual place it points is not right at the surface, but somewhere down inside the Earth. Now, so if you look at this pattern that we get by moving around the Earth, and maybe through space, one thing you notice is that this just looks like a bar magnet. And indeed, the Earth's magnetic field is almost as if it was created by a bar magnet inside the Earth. Let's see if I can draw this here. Here's a bar magnet inside the Earth, right? Something like this. The poles are not on the surface. They're a bit down, and so we get this dip effect. And actually, there are some animals that can, for example, if they live underground, they can figure out which way is up by feeling the magnetic field, because it points downwards. If you take an animal, one such animal, a worm or something from here, the southern hemisphere, it gets confused because the field points the other way. It points upwards. So fun fact, right? If you ever get to do experiments on magnetically sensitive animals, and you take them from a northern hemisphere point to southern hemisphere, they'll confuse up with down. Okay, but so we have this kind of bar magnet shape, and it's ultimately caused by the metallic substances inside the core and mantle in the Earth moving around. This is a so-called dynamo effect, which is actually quite complicated, like what keeps it going and so on. I suggest you take a geophysics class to study that. And more about it. For our purposes, right, we can think of this as a bar magnet that's inside the Earth. That's fairly strong. Now, if you've been paying attention, you'll notice the following. Our compass needle points north, right? That's why we call it this end of the compass needle, like the red end, the part that's painted red, say, the part that has the N on it, we call that the north pole of our magnet. But wait a minute. Which way do compass needles point? They point towards the south pole. They go out of north into south. So if you compare those pictures, you should hold it like this, with the south pole being on top. I do it like this. Right? That's how they look the same. The other, if the north pole is on top, then this would be the wrong way around. So something is wrong. It looks like if I have this bar magnet here in the Earth, the south pole is up here, and the north pole is down here. So south is north and north is south. I hope you see what I'm saying. Alright, if not, pause the video right now and make sense of it. Alright, south is north, north is south. The Earth's magnetic field has its magnetic south pole in the north and its magnetic north pole in the south. The geographic north is magnetic south. Magnetic north is geographic south. Alright, so you've got to distinguish between magnetic north and geographical north. And in addition, the pole isn't actually exactly underneath the geographic north pole, but it sort of moves around over time, like over centuries, millennia, and so on. So I think it's somewhere right now. It's like it's not like here, but the south pole is somewhere under a point. It's more like over here, somewhere north of Canada, in the Arctic Ocean. But crucially, right, the south pole is here, the north pole is down there. So it's kind of wrong way around. Did somebody make a mistake? Could we have made it differently? And the answer is, this is kind of something we can't really get away from, because we called the direction that points north, north, on our compass needle. Makes sense, right? The point, our compass needle that points towards north, we call north, but because unlike charges attract, that inherently means, unlike poles attract, that inherently means that we must call the pole that is in geographical north on the Earth south. Now, had we called this one the South Pole, well, then this one would be the North Pole. So it just, okay, to have this one be a North Pole, if we call this end of the Earth's magnet the North, then our South Pole on the compass needle would have pointed north, which makes sense from a magnetic physics perspective, but I would have confused sailors left, right, and center. Right? It's very intuitive to say the direction it points north is the North Pole of my compass. Except North Poles on compasses point towards South Poles of other magnets. Right. So just something to be aware of. Fun fact might come up occasionally. Just a useful little thing. Okay, so that concludes what I'm going to say about permanent magnets. In part 3 of this, I'm going to move on to talk about how currents and moving charges create magnetic fields. And that'll eventually, the end of it will bring us back to actually explaining these permanent magnets in terms of moving charges. So I'll see you in the next part.